by the end of the 19th century, spectroscopic measurements of sunlight had revealed that the sun contains a large amount of hydrogen and a small amount of helium. Scientists were fully aware of this in the first decade of the 20th century. But with relatively only recently having been introduced and quantum physics still in its earliest development, there was no possibility of applying this observation to the problem of how stars produced energy. This was a complete mystery until the early 1920s, when British physicist Francis Aston discovered that the combined mass of 4 hydrogen atoms was slightly greater than the mass of a single helium atom. Einstein's theory predicted that this difference in mass could be converted into energy, and Aston therefore hypothesized that stars produced energy by fusing hydrogen atoms into helium. This hypothesis was validated over the next 20 years, and the theory of stellar fusion is now regarded as one of the triumphs of modern physics. It was also quickly realized that fusion reactions could produce tremendous amounts of useful energy. Not only that, but the fuel, which is hydrogen, that it would require is so abundant in the Earth as to effectively be limitless, and the only waste product is helium, which is non-toxic and does not contribute to global warming. Atomic nuclei, consisting as they do of uncharged neutrons and positively charged protons, are all positively charged, and therefore they repel each other. However, when the separation between 2 nuclei is comparable to the nuclear diameter, a new force called the strong nuclear force becomes active. Unlike the electrostatic force, which has infinite range, the strong nuclear force has finite range, and strong nuclear interactions will therefore not occur between nuclei that are separated by a distance greater than that range. However, unlike the electrostatic force, the strong nuclear force is attractive and holds protons and neutrons together against a repulsive electric force. 2 nuclei will fuse if we bring them close enough together for the strong nuclear force to overpower the electrostatic force. A positively charged particle of charge lowercase q, like the nucleus of the hydrogen atom, which is a proton, produces an electric field potential given by this equation, where E sub naught is the physical constant called the permittivity of free space. When this potential field tells us that if 2 charges, big Q and little q, are separated by a distance r, then the potential energy associated with their mutual interaction is here. So there's our potential energy. You can see that this energy becomes greater as the distance r becomes smaller. Therefore, in order to bring the 2 charges closer together, we need to perform work on the system of the 2 charges. Imagine trying to force the north poles of 2 bar magnets together. It's possible, but it requires some effort. This diagram tells us the behavior of a ball kicked up a hill for 3 different conditions on its kinetic energy. If the kinetic energy of the ball is less than potential energy, then the ball reaches a height less than h, which would be here. If the kinetic energy is precisely equal to potential energy, then the ball rolls up to the top of the hill and stays. If the kinetic energy is greater than the potential, then the ball rolls to the top of the hill and rolls down to the other side. This diagram shows the total energy of the interaction of 2 hydrogen atoms. If the potential energy is positive, then the protons must do work to reduce their separation, and therefore the interaction will tend to cause the protons to repel each other. If the potential energy is negative, then the protons will have to do work to increase their separation, and so the interaction will tend to be attractive. In this section of the curve labeled by A, only the electrostatic interaction is active and the potential is positive. At a distance of about 1.7 picometers, labeled by point B, the strong interaction switches on and immediately overpowers the electrostatic interaction. The energy at point B is referred to as the height of the barrier, and if the proton starts to the right of the barrier and has energy less than the barrier height, then we refer to the region of the left of the barrier as the classical forbidden region. At distances of less than about 0.7 femtometers, noted by point C, the strong interaction switches from being positive to being repulsive. So a particle on the section of the curve labeled by D will be pushed back to C. The section of the potential curve where the electrostatic interaction dominates, V sub x, for x greater than 1.7 femtometers, is called the electrostatic or Coulomb barrier. So how do we give the proton enough kinetic energy? The simplest and most efficient way is to make it very hot. Of course, temperature is not defined for single atoms, but we can define the temperature for a large sample of hydrogen atoms. We'll call it T. The average kinetic energy for a sample of monatomic gas at temperature T is 3/2 kT, where K is Boltzmann's constant. We find that the temperature required is absurdly high, 6.5 billion Kelvin. Not only is this orders of magnitude above anything that could reasonably be achieved on Earth, but the core of the Sun has an estimated temperature of only about 15 million Kelvin, which is about 0.23% of the temperature we obtained through our naive approach. So how is it that stellar fusion could possibly occur, and how could we ever hope to do fusion here on Earth? If we take one measurement of the position of an incoming proton and find that it is to the right of the Coulomb barrier, with energy less than the barrier height, then there is a non-zero probability of a second measurement finding the proton in the classically forbidden region for any finite value of the barrier height. The calculation, which uses the WKB approximation, we can then find that the equation given the probability is. For the case of the stellar fusion of two protons, we find that assuming that the proton at x equals 0 does not move much during the collision process, with the incoming proton having average energy given the K 3/2 kT, so that E is equal to 1935 electron volts, the probability of barrier penetration is about 1.2 times 10 to the negative 17. This may seem like an extremely small number, but keep in mind that we are dealing with macroscopic quantities of hydrogen atoms. If 1 gram of hydrogen atoms is incident on 1 gram of stationary atoms, then 7.2 million fusion events could be expected to occur. The generic WKB expression depends on E through an expression in the form of V minus E, which might have led us to believe that with a 1 mega electron volt barrier, it would make little difference whether the E was 1 electron volt or 1 kilo electron volt. But in fusion would be just as likely to occur in trees and houses as in the sun. But because the tunneling probability is dominated by the tail of the barrier, not its peak, the final result ends up depending on this tail end, which is 1 over the square root of E. Because P increases extremely rapidly as a function of E, fusion is dominated by nuclei whose energies lie in the tails of the Maxwellian distribution. There is a narrow range of energies known as the gamma window, in which the product of P and the Maxwell distribution is large enough to contribute significantly to the rate of fusion. That is how the WKB approximation plays into fusion. How do we store this very hot reaction? The tokamak reactor is probably the most instantly recognizable of the technologies. The name is Russian and is the acronym for the Russian words for toroidal chamber with magnetic coils, or alternatively, toroidal chamber with axial magnetic field. Developed in the former Soviet Union in the 1950s, the tokamak is the most thoroughly researched and developed style of fusion reactor and remains a leading candidate for large-scale fusion power production. A tokamak reactor has a toroidal or donut-shaped chamber. Magnetic fields are produced by the green coils in the figure and by an electric current conducted by the plasma itself. The resultant magnetic field is helical and indicated by the dark purple arrows in the figure. It is therefore classified as a magnetic confinement reactor. That is, it uses magnetic fields to heat and contain the plasma. Hopefully you can see how that nuclear fusion is possible on the Earth, and hopefully will be an energy source that we can use in the future.